Hi everyone, I'm Yue from Australian National University. Here is our detailed description for our paper. This work is under collaboration between NNU and NVIDIA. We focus on domain shift problem, and here are several examples of domain gap between source training and target testing domains. Row 1 shows image classification datasets with different foreground and background colors. Row 2 is a crowd-counting dataset. One synthetic and another one is a real-world dataset. In both cases, the domain gap between the source and target images is significant and can be clearly observed. In such case, a model trained on source may have bad performance on the target. Much research has focused on bridging the domain gap through changes to image styles, such as color preferences, lighting, and resolution. Here we show several examples about transferring synthetic style to real-world style. The first row is GTF5 to this gap, and second row is VehicleX to vary. We can see this method slightly changes the image, like the lightning, but it seems it does not provide solution to change the content, which might include the density of the buildings, level of occlusion, and the vehicle orientation, as these factors may also influence the result. As a result, we studied the content-level domain adaptation. In this paper, we focus on a smaller and more controllable application, vehicle-ready. The problem is we have a synthetic source and real-world target, so how to remedy such a domain gap? In the first level, the synthetic style and real-world style is different. We may need to perform style or feature alignment. In the second level, it is clear that the target dataset consists mostly of car rears and car front, but it seems the source is not the same. Thus, we study such content alignment. The goal is to let source vehicle image have similar content with the target, like the viewpoint. We introduce a large-scale synthetic dataset VehicleX. It has a diverse range of the realistic backbone models and textures, allowing to be adapted to the variance of real-world datasets. It has 272 backbones including 10 mainstream vehicle types. 16 different vehicle identities are shown here. We built a Unity Python interface, which allows us to modify attributes of the environment and the vehicles, and obtain rendered images. To explain, we adjust the vehicle orientation, light direction and intensity, camera height, and distance between the camera and the vehicle. When VehicleX data is used for real-ID model training, we also add random real background and distractors. We show comparison of some real-world and synthetic vehicle real-ID datasets. VehicleX has detailed vehicle labeling, and its identities are different 3D models, thus can potentially render an unlimited number of images under different environment and camera settings. We focus on vehicle real-ID tasks in this paper, but our proposed 3D vehicle models also have potential benefits for many other tasks. VehicleX is released open source. We propose an attribute descent approach to approximate attribute distribution in real-world datasets. The workflow is shown here. Given a list of attributes and their values, we use a render for vehicle simulation. We compute the threshold inception distance between the synthetic and real vehicles to indicate their distribution difference. By updating the value of attributes using proposed attribute descent algorithm, we can minimize FID along the training iterations. The simulated data with learned attributes in the bottom right corner will be used for real-ID model training. Specifically, we manipulate each attribute in VehicleX in a brute force manner, aiming to minimize the discrepancy between VehicleX and real data in terms of the FID score. From the figure in the left bottom, the real-ID accuracy successively increases and FID consistently drops during the attribute descent. From the scope of FID curve, we can see the orientation has the largest impact on the distribution difference. Lighting is the second most impactful, and the camera attributes are the third. Top of this slide shows synthetic vehicles in each iteration. We initialize attributes by setting orientation to the left, the light intensity to the dark, light direction from the west, and the camera height and distance to its smallest value. We can see our source synthetic dataset gradually approximates target attribute distribution in the order of orientation, lighting, and camera settings. The major benefit of VehicleX is to join training with real-world datasets. We use rank 1, rank 20, and MMP as evaluation metrics. Here we show method comparison on CityFlow dataset. Here is a current state of art on CityFlow dataset. R means training with real data only, and R plus S denotes a joint training with synthetic data. Then, here is our baseline model, which uses real-world data only for the training. It is built with a combination of the cross-entropy loss and the triplet loss. Here, we simulate data with random attributes and then mix them with real data. When performed joint training, there is a significant improvement over baseline. Then, our learned attribute using attribute descent further improves the result. VehicleX with learned attribute has been used in CVPR AICT Challenge 2020. We further compare learned attributes and random attributes in joint training. We present MAP and show such improvement is consistent on 3 datasets. This is the end of our introduction to our paper. You might find more details in our paper and code. Here we also introduce our ALICE benchmark suite, which is an online evaluation server on domain adaptation tasks. Now the first version of ALICE has been online, now accepting submissions. The task is style official level domain adaptation from synthetic persons to real persons. Our VehicleX will also be part of this benchmark in the future. Tasks on semantic segmentation is also on the way. Visit our website for more details.